Hello, my name is Sonya. Welcome to today's edition of Science Daily. Today we will be discussing the history and nature of plants and their pigmentation. We will also be consulting with Dr. Fitzgerald, as she is a specialist with plants and their pigmentation.
Good afternoon, Sonya. I'm glad you invited me to be here today. I'm excited to discuss my exploration with pigments further. As you can see, there are plenty of photosynthesizing organisms around us.
Exactly, but let's start at the beginning so we can give our viewers a basic knowledge of plants and their pigmentation. It's fascinating how the varying amounts of sunlight as a result of seasonal changes cause the more prominent pigment, chlorophyll, to disappear and the other minor pigments to be expressed. This obviously is a representation of how leaves change color in the fall.
Right. As leaves begin to die in the fall, chlorophyll rapidly begins to decompose and thus allows minor pigments to be expressed, which result in the beautiful displays of color that we see in the fall.
Yes, I am from Pennsylvania, and I find that these color displays are especially beautiful in the northeastern parts of the United States, where there are rolling hills and a multitude of deciduous broadleaf trees.
That is very true. As you can see here in sunny Florida, the change of color in the leaves is not often seen, as the weather is very temperate in the fall and winter, and thus it is uncommon to see any major changing of the leaves.
So, being from the Sunshine State, how is it possible that you can study plants and their pigments when it is so uncommon to see an abundance of leaves changing color?
Well, that's very true, but my latest research, however, focuses on spinach leaves and which pigments it contains. Most plants, spinach included, contain a number of pigments that can fall into two general classifications of pigments. Those two classifications include chlorophyll, and carotenoids. Chlorophyll A is expressed as in a blue-green color, while chlorophyll B is expressed as bright green. These pigments are conjugated and thus capture all the non-green light, which is used for photosynthesis, as is the case with any plant. Then there are carotenoids, which includes pigments that range from colors of red to orange-yellow.
Very interesting. So obviously the major pigment, the one that is expressed for most of the year in plant leaves, is chlorophyll, and the minor pigments, which are not expressed most of the year, are the carotenoids. Now, from my knowledge, spinach leaves contain mainly chlorophyll A, chlorophyll B, and beta-carotene, and some smaller amounts of xanthophylls. Is this correct?
Yes. Xanthophylls are just oxidized versions of carotenoids, so it is interesting to note that these minor pigments play a secondary role in photosynthesis. This occurs when the minor pigments transfer their energy that they absorb to the chlorophyll A, so that the energy can then be used in photosynthesis.
Plants are remarkably efficient organisms.
Very true. Some of my earlier research focused on the characteristics that are unique to each of the pigments contained within spinach. An example of this research was on spinach pigments and their differences in polarity. Each pigment has a unique polar or nonpolar quality based on its molecular structure.
Ah, yes. For example, I know that beta-carotene is a hydrocarbon and is therefore nonpolar.
Oh, correct. And in contrast, the chlorophylls contain a number of carbon to oxygen and carbon to nitrogen bonds, making them polar. However, the difference in polarity between chlorophyll A and chlorophyll B is very slight.
That makes sense because structurally chlorophyll A has a methyl group in a position where chlorophyll B has an aldehyde, which makes chlorophyll B only slightly more polar than chlorophyll A. Knowing the relative polarities of each pigment must have great value as far as experimentation with spinach pigments is concerned.
Oh yes, that has been the bulk of my research. I've been using spinach in the lab to see how these pigments separate.
That is very interesting to me. I know that there are several methods of separating components of a compound. I have used liquid-liquid separation through the use of a separatory funnel, distillation, recrystallization, vacuum filtration, and column and thin layer chromatography. So, was there any technique in particular that you preferred to use for your research with spinach pigmentation separation?
Absolutely. I almost exclusively used column chromatography and thin layer chromatography for my research because it seemed to be the most efficient method of separating the pigments and exploited the unique polarity of each pigment as we mentioned earlier.
That is understandable because in my experience, column chromatography seemed to be relatively time efficient and the RF values experimentally obtained can be directly compared to standard RF values of the pure pigments.
Exactly. Before we go into greater detail about my experimentation, I would like to give credit to the original developer of chromatography, Michael Svet.
Of course, he was the Russian botanist who first developed chromatography in 1903 by producing a separation of plant pigments through a column of calcium carbonate. However, since his experimentation with plant pigments, chromatography has been used less and less to separate colors and more to identify components of a compound. But the same principles still apply.
Yes, without SPET, we would not have this valuable technique for separation of compounds, and now that we know how it began, we can explore how column chromatography works.
Yes, as we mentioned previously, column chromatography takes advantage of the unique polarities of each pigment. Column chromatography works based upon the principle that a solvent is allowed to run through a mixture and the molecular components travel with the solvent at different rates.
That is correct. The components are separated because the greater the attraction between the molecules in the absorbing medium, commonly silica gel or alumina, for column chromatography, the slower the molecules elute. In addition, the higher the solubility of the components in the solvent, the faster and therefore the further the molecules will travel.
Because of that, one of the advantages of column chromatography is that you can change the solvent that is being passed through the mixture in order to separate out the components. For example, you could start with a nonpolar solvent to separate out the nonpolar components, and then increase the polarity of each successive solvent added so that you can separate the more polar components.
Furthermore, the more polar components elute slower because the absorbing medium is also polar. The components will therefore stick to the absorbing medium and resist movement with the solvent until the solvent introduced is more polar than the absorbing medium.
Great! Now let's relate all of this information to your experiments in particular. To do this, we actually completed a spinach pigment extraction experiment together so that we can compare and evaluate our results with your previous research. Let's head to your office and discuss our experiment and the results in greater detail. Okay, so let's start off by explaining the methods and materials used in the experiment.
Of course, there's a certain amount of prep work that must be completed in order to obtain the extract needed to complete column chromatography. First, I used a mortar and pestle and a little bit of acetone to grind up the frozen spinach in order to lyse all of the cells so that the pigment can be effectively identified.
Then we ran the mixture through a centrifuge twice. This will concentrate the extract more by separating the solvent, water, and pigments, and leave the organic matter at the bottom. The pigments will rise to the top because they are less dense than the organic material. It is important that the top aqueous layer was dark green because that indicates that the cells were lysed effectively and the pigments were present.
So it makes sense that after the extract was formed, you would put a drying agent in the solution, such as sodium sulfate, commonly used for that purpose, to rid the solution of water and solvent. Then, of course, the next step was to select the solvents that would be used in order to separate out the components of the mixture based on polarity.
Yes, of course. We selected 3 solvents: pure hexane, a 7-to-3 hexane to acetone mixture, and pure acetone to separate the pigments from the extract. Hexane was used first because it is nonpolar and should elute the nonpolar component beta-carotene through the column first.
We used 7-to-3 hexane acetone mixture second because it is more polar than hexane and would therefore begin to separate the slightly polar components like xanthophyll.
Last, we used pure acetone because it is the most polar and should cause the most polar components, chlorophyll A and B, to elute through the column.
Now there is more to the story when it comes to choice in solvents. These solvents were not only chosen for their polarities because there are many solvents that have proper combinations of polarities and to elute the pigments. These solvents were chosen because of their inherent greenness.
Yes, we cannot forget the importance of green chemistry when it comes to performing scientific experiments. These solvents are safer and less hazardous than the other solvents that have been used in the past for the same purpose. The most hazardous aspects of hexanes and acetone are that they are slight irritants to the skin and lungs if inhaled. However, these hazards are minimized by conducting the experiment under a fume hood and wearing goggles and gloves.
All that is correct, and there are a number of other aspects of this experiment that make it very green, but we will talk about these in more detail later, because I cannot wait to talk about the experiment in more detail. So we have chosen the solvents, and the next step is to set up a column in which the separation will occur. In order to set up a column chromatography, first a small piece of cotton needs to be pushed down into the bottom, and then a small amount of sand is added. On top of the sand, 6 inches of powdered silica gel will be added to the top. Then sand was added, followed by hexane, which allowed it to flow through the column and pack the silica. Once the hexane was just above the sand, we added the extract.
To get the separation started, we again added hexane, which should cause the yellow band of carotenoids to elute through the column into a collection test tube. Once this was eluted, the collection test tube was switched to collect the next eluent, which should have been xanthophylls by the use of 7-3-hexane to acetone mixture. We switched the collection test tube again and collected the most polar pigments, which should have been the chlorophylls that appear as a green band. Once these pigments were separated, we could then concentrate them by putting them in a hot water bath for a few minutes.
And once concentrated, we could then analyze our separations through TLC, or thin layer chromatography. Of course, what we believe should occur in theory is not always what happens in practice. When we actually completed the experiment, we were unable to physically visualize the elution of the yellow band. Thus, we were forced to collect all of the elution in the first test tube until we saw that the green band was at the bottom of the column, at which point we switched to the second test tube so that we could at least collect the green band totally separate from the other pigments in the first test tube.
Even so, we ran a TLC by spotting each test tube. We found that there was a separation of pigments within each test tube. For example, a TLC of the first test tube produced RF values of 0, 0.275, 0.518, and 0.583. These RF values could be directly related to the standard RF values for the pigments in spinach, which are widely accepted in literature. For example, the RF value of 0.275 would correspond to a separated xanthophyll because the literature RF value for xanthophylls is 0.35.
And another test tube that was a collected fraction from the experiment contained a similar RF trend with 0.324, 0.485, and 0.641, corresponding respectively to xanthophyll, chlorophyll B, and chlorophyll A. RF values based on polarity, and the farther it travels on the plate, the less polar the molecule is. Therefore, the most polar compound is xanthophyll. I found it very interesting that the two important fractions we contained multiple pigments within.
We also completed several trials and picked the one trial that singularly represented the expected findings most accurately. We did multiple trials as a comparison to yield greater results.
Now we should conclude with some possible sources of error that could have contributed to the variance in RF values that we obtained. When we set up the columns, I noticed afterward that it would have been a good idea to add more extract to the top of the column so that there was a greater source of pigment. Maybe then the yellow band of beta-carotene would have been visible. Sonya and I also created the silica gel in the column versus outside of the column. I don't know if this would have made much of a difference or if the band was able to travel farther down the column. Sonya, can you think of any other possible sources of error?
Yes, I think one possibility is that the fractions were not as concentrated as we would have liked them to be. We would have received better TLC results if the fractions containing the pigments were concentrated, possibly through air streaming. If I was to do this experiment over again with you, I think a different TLC solvent could have been used, because no color band was visible when it should have been, to indicate qualitatively which pigment is present and how far the band traveled up the plate.
I'm very appreciative for the time I've spent. I've been able to share with the viewers and tell them about our findings and inspire them to get into the lab and do creative research like we've done.
So, what can we learn from today's episode? We can learn how the ability to separate out molecular components of a mixture is a valuable skill that can be used in organic chemistry labs. More specifically, the ability to separate plant pigments using column chromatography enables chemists to study the characteristics and nature of different plants. We have learned that column chromatography is a relatively green technique that, because the reagents used have a low toxicity, the byproducts are harmless, and the solvents can be recycled. Thank you for your time, Dr. Fitzgerald. We'll see you next time. Great. Now let's relay all of this information to your experiments in particular. To do this, we actually completed a Pigment. Great. Now let's relay all of this information to your experiments in particular. To do this, we actually completed a spinach.
Yes, without sweat, we would not have this valuable technique for separation of compounds. And now that we know it... Furthermore...
No,
let's go.